GameSci.com. GameSci.com. Welcome to GameSci.com. I am Professor Chris Ferguson.
Hiya, we're back. The topic of this lesson is abstract classes, abstract methods, interfaces, and a little more polymorphism thrown in. What is an abstract class? It's a class designed specifically as a parent, base, or superclass. They do not create direct object instances. They exist as child objects. Abstract classes make polymorphism even more powerful. I'm showing you here a generic class diagram here, and you can see that a concrete class inherits everything that an abstract class has. Now, the only difference between a concrete class and an abstract class is you build direct objects out of concrete classes. You never build direct objects out of abstract classes. Abstract classes are designed for inheritance. Using the keyword abstract when creating the class makes it an abstract class. You can see here at that top line, public abstract class, abstract class. All we've added is this extra word, and we're declaring that we want this to be an abstract class. What does that mean? Well, the first thing it means is we're designing this class to do inheritance. The primary purpose of an abstract class is to be the parent class when doing inheritance. Use the extends abstract class to create one or more new classes from an abstract. If you are not doing inheritance, there is no reason to create an abstract class. This is the purpose of an abstract class, to extend it or inherit from it. This is something you definitely want to do with an abstract class. Extend it. What you don't do with an abstract class is build direct objects out of it. You can see this line of code, abstract object equals new abstract class. You do not use the new operator on it. A direct object instance is not created from an abstract class. Never use the new operator in front of an abstract class. Remember, abstract classes are for inheritance, not for creating direct objects. So, how do they become objects? Polymorphism means you can assign a child class object to a parent class reference variable. That's how an abstract class becomes an object. The object built from the child will have all the variables and methods of the abstract class, so it can be assigned to a variable of type abstract class. So look at that solid red double-sided arrow there. The child extends abstract class. When I build a new child object, I can assign it to an abstract class variable. Now, this is a generic example of creating and using an abstract class, but it's important to understand the idea behind it. When I build the child object, you can see obviously that the child object is going to have the child variables and the child methods. That's a duh. However, it will also have the abstract class variables and methods. Because the child extends abstract class, we will have every one of abstract class's variables and methods, which means we can certainly assign the child object to an abstract class reference variable. Now let's look at a specific example of creating and using an abstract class. These are code snippets. I'm not showing you the whole program. I'm showing you the pieces in order to create and use an abstract class. Using the keyword abstract when creating the class makes it an abstract class. Enemy, in this case, public abstract class enemy, is going to be an abstract class. Now we know from inheritance we should place the common or share code in enemy, and then all the child classes like vampire, drone, etc. inherit from it. We also know from inheritance that we should put specific or unique code in child classes. Examples like neck biting goes in the class vampire because that's what a vampire does. Let's create an abstract class enemy to be parent class to every enemy object we plan to build. First one we'll create is vampire. Public class vampire extends enemy. That's exactly how you use an abstract class. Use the abstract class enemy to create vampire and many other classes including drone, mutant, etc. A boring game has 2 or 3 opponents. An interesting game will have 10 to 20 different opponents. Build many from enemy. Anything that tries to hurt or damage the main character should inherit the abstract class enemy. Now that enemy is an abstract class, what don't we do with it? A direct object instance from abstract class enemy can never be created. Do not do this. This is an example of what not to do. Reason number 1. The compiler will refuse to compile any code instantiating an abstract class. This line of code would light up in red and refuse to compile if you tried to create an object out of class enemy. Reason number 2, enemy is incomplete. It needs specific code from vampire, soldier, etc. in order to be a complete object. So we're not allowed to build objects out of abstract classes. So what are we allowed to do with abstract classes? We are allowed to assign child objects to abstract class reference variables. So we're going to create this enemy object and set it equal to new vampire. Remember, vampire extends enemy, so through inheritance and polymorphism, it's certainly legitimate to assign a child class object to a parent class reference variable. Polymorphism means you can assign a vampire class object to an enemy class reference variable. The object will have all the variables and methods of enemy. Get used to it. Almost always, when using abstract classes, child objects are assigned to parent class reference variables. It's what we do with abstract classes. So I've built this new vampire object and I'm showing it to you on the screen. And of course, since it is a vampire object, it will have vampire variables and vampire methods. That's a duh. But it will also have enemy variables and methods because vampire extends enemy. Since it has all the enemy's variables and it has all the enemy's methods, you can certainly assign a vampire object to an enemy class reference variable. Let's do one more. Let's create a public abstract class shape. There is a pattern here. We're going to create an abstract when you plan to create multiple similar child classes. In the case of shape, we plan to build circles, rectangles, triangles, and other shape objects out of shape. In the case of enemy, we're planning to build multiple child classes like vampire, drone, mutant, etc. If we were building a parent class gun, we were planning to build child classes like pistol, shotgun, and rifle out of it. Remember, inheritance is used when you want to create multiple classes, but very related multiple classes. Circles, rectangles, and triangles are very related. Vampire, drones, and mutants are very related. So that's when we want to think about creating abstract classes, is when we're creating multiple classes of related types. Follow the pattern here. We're going to do the same thing we did with enemy, except we're going to do it with class shape now. We built the abstract class shape, so then let's have circle extend shape. That's what we do with abstract classes. We extend them or inherit them. The pattern, the subclasses extend or inherit from the abstract superclasses. Subclasses have the specific elements. For example, circle will have a radius, rectangle would have a width and height. Abstract superclass would have the common or shared elements like X position and Y position. If you want to draw a circle on the screen, you need 3 pieces of information. You'll need an X and Y position, which you can inherit from shape, and you'll need a radius, which circle has, and then you can draw a circle. When you're ready to draw a rectangle on the screen, you'll need an X and Y position, which you inherit from shape, and you'll need a width and height, which rectangle has. Remember, common or shared elements go into the parent class shape. Specific or unique elements will go into the child classes circle, rectangle, and triangle. Again, notice the pattern. We have these derived class objects that are almost always assigned to base class variables or even better, arrays. So here's an example using an array. I'm going to start assigning these shape objects to this array called screen. Any derived class that extends shape, circle, rectangle, triangle, is assigned to any array slot in this array screen. Fill the array with objects and then use a simple loop to draw the screen. So screen subscript 0 equals new circle. Everything drawn on the screen is an object from this array. Since a circle object has all of shape's variables and all of shape's methods, it can be assigned to a slot in the shape array. Each screen or level of the game is composed of different shape objects. That's what we're going to do. We're going to fill up this array with shapes, and when we're ready to draw the screen, we'll build our virtual world. Screen index number 1 equals new rectangle. Here's the beauty of this pattern. Even during gameplay, you could add something to the array and bam, it shows up on the screen. You can remove an object from the array and bam, it goes away. If during the game you wanted shapes to disappear after they were knocked down, all you have to do is take them out of the array and they'll no longer be drawn on the screen. If you want to add new elements, just add them to this array and they'll show up on the screen. But wait, there's more. The real power of abstract classes comes from abstract methods, and those are next. Abstract methods. What is an abstract method? It's declared in the parent and written in the child class. In other words, it's prototyped in the superclass and implemented in the subclass. It's the parent class forcing the child class to do something. For example, what chores does your dad make you do? Does dad make you wash the car or mow the lawn or clean the room? That's what dads do. They make their kids do stuff. I want you to do these chores or no playing video games. A little abstract class diagram here. And what does an abstract dad do? Well, abstract dads issue orders. They say, you, kid, wash the car, mow the lawn, or no more playing video games. Then what does the child object do? What does the child you do? Well, you complain. You complain that you have to wash the car and mow the lawn. And because you want to play those video games, you go ahead and do the chores that dads insist you do. Abstract classes are no more different than abstract dads. Abstract classes issue orders. They order the child class. I want you to write a move method. I want you to write an attack method. And if you don't do that, I will not let you compile. The concrete class, again, the concrete classes are the ones we build objects out of. The concrete classes complain and say, well, I have to write the move method. I have to write the attack method. That's all an abstract method is, a method declared in the parent class that the child class is forced to do. If your parents have ever made you clean your room, you understand what an abstract method is. So let's look at an example of building an abstract method. I'm going to build a public abstract class enemy here, and I'm going to strip out a lot of the extra code so you can just see the abstract classes and what the abstract classes do. In order to create an abstract method, you have to have an abstract class. It's a requirement. Any class with at least one declared abstract method is abstract automatically. Now we put the keyword abstract on class enemy, but the mere fact that we declare abstract methods in the class will also make it abstract. Inheritance says common or shared code belongs in the parent class, and specific or unique code belongs in the child class. All enemy objects are going to attack. That's what makes them an enemy. But don't they attack differently? I want my vampire to attack. I want my drone to attack. I want my soldier to attack. But they're all going to have a different way of attacking. And abstract methods allow us to do that. Public abstract void attack semicolon. Notice the semicolon. This is an abstract method attack. It's declared or prototyped in the parent class. Any child class must write that method or the child class will not compile. The keyword abstract is required on this line. The class enemy is insisting that all child classes, zombie, drone, soldier, vampire, etc., provide their own version of the attack method. For example, a zombie will try to eat your brain. That's what zombies do. A drone will fire a missile. A soldier will shoot a gun. That's where we use abstract classes. We know every enemy object wants to attack the main character, but they're all going to do something slightly different. So we declare attack to be abstract in the parent class, guaranteeing that vampire will write an attack method that bites the person's neck, or zombie will write an attack method that tries to eat your brain. Let's do it again. Public abstract void move. Notice the semicolon again. We're not writing the method move here. We're declaring the method move, or we're prototyping the method move in the parent class. Inheritance says that common or shared elements belong in the parent class, and we want all enemy objects to move. So we're going to declare an abstract move in the parent class. The zombie moves in a slow, dim-witted manner. A drone flies, hovers, moves up and down. A soldier walks, jogs, runs with a purpose. They all move differently. And inheritance says specific or unique elements belong in the child class. So write a move in the child class and make it behave as that object would move. So the move method in zombie would move in a slow, dim-witted manner. The move method in drone would fly. The move method in soldier would react like a soldier. We want all enemy objects to move, so we declare an abstract method move in the parent class, but then the child class can customize or make specific the move for a particular class. Objects should always behave like the thing they represent. A zombie should act like a zombie or move like a zombie. There will be other enemy stuff in this class. Once again, I strip out the extra code so you can just see the abstract methods. To be clear, this is not the entire enemy class. Just the essential elements to declare an abstract method are shown. There's not enough room to also list things like X and Y position, etc., and all the other variables, the get and set and all the other methods. I can't show you all of that in one screen, so I strip it out and just show you the essential elements. But they are there. Move will be using them to change the location of the enemy object on the screen. Keep in mind that this is a hollowed out enemy class. All the other stuff we've talked about, like X and Y position and the health variables, they're all still there. I just can't show them all on one screen. Let's create a public class zombie that extends enemy. Hopefully it is obvious. To use an abstract method, a child class is required. When zombie inherits enemy, it is required to write the abstract methods declared in enemy. This is a rock solid guarantee. Zombie will not compile without the abstract methods declared in enemy, attack and move. Plus any other class that extends enemy will also have these guaranteed abstract methods. If shark extends enemy, then shark will have an attack and shark will have a move method. It is a requirement for all child classes to implement the abstract methods. Notice the double-ended arrow that I put in here. The declaration of the abstract method attack in the parent class enemy means zombie is required to write or implement a method. The appearance of the attack method in class zombie is not an accident, it is a requirement. Plus any other class that extends enemy, drone, soldier, vampire, etc., will also have the guaranteed attack methods. The fact that the parent class declares it to be abstract means the child class is required to write that method. When a zombie attacks, it tries to eat your brain. It's what they do. The attack method in zombie should implement brain eating. In the class drone, the attack method should launch a missile. In the class vampire, the attack method should bite a neck. In the class soldier, the attack method should fire a gun. It's very important that child objects behave like what they're representing. Child classes contain the specific code, and brain eating is very unique to a zombie. So make sure the attack method in zombie acts like a zombie or attacks like a zombie. Notice the double-ended arrow again. We're going to write a public void move inside the class zombie. The declaration of the abstract method move in the parent class means zombie and all other child classes are required to write or implement the move method. Inheritance says common or shared code belongs in the parent class. All enemy objects move, so it's declared in the parent class. Inheritance says unique or specific code belongs in the child class. All objects move differently, so it's implemented in the child class. Make sure the move in the zombie class behaves like a zombie. Zombie must write the move method, it's a requirement. A zombie moves in a slow, dim-witted, dragging a foot manner. The move method should reflect this behavior. In class tiger, the move method should stalk at first, but go much faster when chasing prey. In the class drone, the move method should fly, hover, go up and down. If 10 classes extend enemy, then you will write 10 different move methods, and each method should behave as expected. If you built a class landmine that extend enemy, then the move method might even be empty. Landmines just sit there. They don't change their position. So it is perfectly legitimate if I wrote a class landmine to have a move method that was absolutely empty, did nothing at all, because I don't want that landmine to move. Again, the most important thing is for the child objects to behave like the thing they represent. A tiger object should move like a tiger. A zombie object should move like a zombie. And a drone object should move like a drone. There'll be other zombie stuff in this class. This is not a complete class. To be clear, this is not the entire zombie class. Just the essential elements to implement the abstract methods are shown. There's not enough room here to also show the other zombie specific code like moaning brains when they want to feed or coming back to life after they're killed. There'll be other code in this class. We just haven't shown it because it doesn't fit. Any variable or method specific to zombie would be here, in addition to the required abstract methods. Because attack and move were declared abstract in the parent class enemy, then attack and move must be written or implemented in any child class that extends enemy. Let's go back to our shape example and see how it would work with shape. We're going to create an abstract class shape. This is an example that uses inheritance, polymorphism, and abstract methods. Class shape will be the parent class to anything we want to draw on the screen. In a 3D game, we'd probably build the screen using things like circles, triangles, and rectangles. But in a simple 2D game, like a Mario style game, we could use elements you see on the screen, like a house or a tree. There's no reason a shape has to be a circle or a rectangle. A shape could be anything. It could be a house or a tree. What we're going to do is build an array of shape objects and see how they get on the screen using abstract methods. This is code snippets. I'm just showing you 2 lines from class shape. Public abstract void draw. You're going to want to make sure to put an abstract draw method in the shape class. That means any class that extends shape must implement a draw method. The abstract method draw will make sure everyone that extends shape has a draw method. Kind of important because these will be the objects we want to draw on the screen. This array was declared somewhere else. This again is a little piece of code. It's not a complete program. We're going to create this shape array screen and set it equal to new shape 500. The array is key At the start of each level of the game, you load the array with the objects you want shown on that level. That way, one program can display many different level screens. Building a new level is as easy as loading a different list of house, tree, or cloud objects into the array. This array is going to get what we want to put on the screen: houses, trees, and clouds. Once we have an array loaded with houses, trees, and clouds, which I've shown down below, we're going to write a for loop to go through and draw all these things on the screen. It's very simple. Start at the beginning of the array or the list of objects we want drawn on the screen and go through every object calling the draw method. And since draw is abstract, you're guaranteed that it will be there. I less than num shapes. The variable num shapes will track how many different objects are currently in the array. Let's say a level only has 100 objects. You don't want to loop 500 times if there's only 100 objects on it. So num shapes will contain 100 and stop the loop after the 100 objects. Since I less than num shapes was very true, it went in and executed the code inside the for loop. We got screen subscript of I dot draw, execute the draw method for the object in slot 0 of the array. This will go to the object in slot 0 of the array and execute its draw. Since it's abstract, it automatically executes the draw in the house class. That's what I'm showing with the arrow up here. If shape calls draw, it'll go down the line and execute house's version of the draw. Using a variable like x and y position, which would come from the shape variables, and the fact that we're a house object, we can draw a house on the screen, and it will go in the correct spot. Spinning back up in the loop, I++, changing the variable I to 1, will move to the object in the next slot of the array. When I is 1, it means we want to access this cloud object. 1 less than num shapes is still going to be a true statement, so the loop will execute again, and we'll go down and do the draw routine. Now, what happened when we went to slot 1 to do a draw? Again, in slot 1, we just happen to have a cloud. That's what this diagram is showing you. Go to the object in slot 1 of the array and execute draw. Since it's abstract, it automatically executes the draw in the cloud class. Using variables like x and y position, which are part of the object from enemy, and the fact that we want to display a cloud, we can draw a cloud at any position on the screen. I++ will change the variable I to 2 and we'll move to the object in the next slot of the array. As soon as we advance I, we're advancing to this third object, the one in slot 2. I less than num shapes. At this point, this is still a true statement because we have plenty more shapes left to go. So the loop will execute again. Screen subscript I, which is 2, dot draw. This will go to the object in slot 2 of the array and execute draw. Since it's abstract, it automatically executes the draw routine in the tree class, using variables like x and y position that are part of the object to place it in the right spot. In order to draw anything using this scheme, you're going to take some common variables that come from class shape, and then the local variables, the specific variables that come from class tree, and draw the tree on the screen. I++, changing the variable I to 3, will move it to the object in the next slot of the array. You can see where the arrow is saying, okay, I'm pointing to the same object as slot 3. I less than num shapes, at this point, still a true statement, so the method executes again. Screen subscript I dot draw. It will go to the object in slot 3 of the array now and execute draw because I has the value of 3. Since it is abstract when it calls draw, it automatically executes the draw method in the house class, using variables again like x and y position that are part of the object to place it in the correct spot. So there was a simple loop. On 4 objects, we can't build a very spectacular screen, but what if I had 40 objects or 400 objects? I could draw a pretty elaborate screen if I had 400 objects in my screen array. You get the picture? Pun intended. At this point, the loop would continue down the array, drawing more objects. When used together, inheritance, polymorphism, and abstract classes/methods means very simple code can generate amazing screens. That tiny little loop can build a spectacular video game screen. Inheritance levels. Inheritance can have many levels. Abstract methods determine if you go up or down a level when trying to locate a variable or method. Instead of just having a child that inherits from a parent, we could have a parent that inherits from the grandparent. Now remember, the child picks up all the variables and methods of the parent, but also gets all the variables and methods of the grandparent. Inheritance is not free. One of the downsides of doing inheritance is you use up a lot more memory. Let's look at an example of this. Let's create a public abstract class enemy. And inside our public class enemy, we're going to have an abstract move. Using the keyword abstract when declaring, note the semicolon, a method means a child class must write or implement the method. Got that? Parent classes declare or prototype methods. Child classes write the specific implementation. Public class soldier extends enemy. Because soldier extends enemy, it is now required to write that move method above. Soldier will not compile without that move method above. A soldier object should behave as expected and walk, march, or run when the move is called. Well, the only way for that to work is if every child class implements a move method. And the abstract move method guarantees every child class implements a move method. Public class sniper extends soldier. Now sniper is a special type of soldier, so it extends soldier to inherit name, rank, and serial number, but a sniper does not move. They hide or camouflage in one spot. In this case, the move method in sniper could be empty or just sets the same X and Y position and behaves like a sniper. See our three levels of inheritance? Sniper extends soldier, soldier inherits enemy. Soldiers move, so their move method should have that soldier working its way around the screen. Snipers stay in one spot, so its move method should not change anything to do with the X and Y position. Let's build a sniper object. Sniper object equals new sniper. A sniper object will have the variables and methods for all three classes, including two move methods, from class soldier and from class sniper. Also note it's being assigned to the reference variable of type sniper. I'm building a sniper object and assigning to a reference variable of type sniper. Well, of course, sniper is going to have all of sniper's variables and methods. Those are listed in green. But sniper extends soldier, so it will also have all of soldier's variables and methods. But soldier extends enemy, so we'll also have all of enemy's variables and methods in this sniper object. In the end, it's a three-part object. It's part sniper, it's part soldier, and it's part enemy. Now that I have my object created, I said go to my sniper object and set its X position to 400. What if set X position wasn't part of the sniper class? Variable object is type sniper. It looks at the class sniper first to see if the method is there. If it does not find set X position in class sniper, it will move up the ladder and look for it in the parent class soldier. Still trying to run the method set X position. Set X position is not in class soldier, so it'll move up the ladder and look for it in the parent class enemy. That's what happens. I go to the sniper object to execute a method. It's not there, so I move up to soldier to execute the method. It's not there, so what am I going to do? Keep moving up the line. In order to execute set X position, I tried sniper, it wasn't there. I tried soldier, it wasn't there. I'm going up the line here trying to find the set X position. Method set X position located and executed. in the enemy class. It was inherited from enemy. This is standard behavior for a normal method. Move up the inheritance hierarchy to locate and execute a method. If a soldier object tries to run setX position, it tries it in soldier first and then moves up the line to enemy. And of course, setX position is passing 400 as a parameter, so that's what I imagine the X position value gets set to. Now the next line of code says enemy same equals object. This line of code does not create an object. It simply declares another reference of type enemy and points it to the same object created above. References, object, and same point to the same object. This line of code I have underlined does not build a new object. So I can go through either variable. I can say object dot and execute something in this object, or I can say same dot and execute something in this object. In fact, let's do it. Let's do a same dot move. The reference variable same is of type enemy. To execute the method move, it starts at class enemy. And what does it see? It sees that it's an abstract method in enemy. And what does it see? It sees there's an abstract method in enemy called move, so it will start going down the ladder. Whenever something's declared abstract in a parent class, it means I need to go down the ladder looking for it. Normal methods go up the ladder from sniper to soldier to enemy. Polymorphism methods go down the ladder from enemy to soldier to sniper. Since down the method move is abstract, it'll go down the inheritance hierarchy to run the method. In fact, it goes all the way down the line. There was a move method in soldier, but since it's abstract, it'll go all the way down to the child class and try to execute it. Since sniper wrote a move method, it will skip soldier and go all the way down the ladder. We're still executing same.move. We're going down the line looking for the move method. Since the method move is abstract, it will go down the inheritance hierarchy as far as it can to execute the method. In sniper, the move method does nothing. This is called overriding, since a sniper should stay in the same location. Alright, let's wrap her up. A normal method moves up the inheritance hierarchy looking to execute a method. An abstract method moves down the inheritance hierarchy looking for the method to execute. Normal method, I'd start at sniper, and if it wasn't there, I'd go to soldier, and if it wasn't there, I'd go to enemy to try and run that method. An abstract method, I'll start at enemy and look to run it. It's abstract, so I'll move down to soldier. Soldier may have that method, but it's got a child class. I'll look at that and see if I can run it from the child class. Interfaces. A way for unrelated objects to communicate. Sort of like inheritance light. Another way you can think of it is it's like a pure abstract class. In this generic diagram here, I have class object A, which of course is going to have the object A variables, and it's going to have the object A methods. But it's also going to have some interface methods. If it has object A's methods and interface X's methods, then I have a completely separate class, object B. It's going to have object B variables. It's going to have object B methods, and it's going to have what's called interface X methods. Both object A and both object B implement in the same interface. These two objects can talk to each other. Object A and object B talk by calling interface X methods. Public interface explode me. The keyword interface is used to create explode me. An interface is like a pure abstract class. Similar to an abstract class in that any class that extends an abstract class must write the abstract methods. Any class that implements an interface must write the abstract methods. And an interface is essentially a list of abstract methods. Inside the interface, I'm going to say abstract public void do explosion. Notice the semicolon at the end. This is a declaration of a method do explosion. Note the semicolon. Any class that implements the interface must write it. You cannot declare an instance variable in an interface. Interfaces do not have variables. Interfaces don't have real methods. Interfaces only have abstract methods. Don't write any normal methods in interface, only abstract methods. When I say it's like a pure abstract class, doesn't mean it is an abstract class. It just means an interface can only have abstract methods listed in it. We're going to create a public class zombie that extends enemy and implements explode me. What you do with an interface is have classes implement it, which means zombie must then write do explosion. Explosions are an integral part of video games. Class zombie must write a method that animates what happens when a zombie gets hit by a grenade or steps on a landmine. Class house extends shape and implements explode me. What you do with an interface is have a class implement it, which means house must write do explosion. If only enemy objects blew up, would not need an interface. But house or other elements that appear on the screen might get hit by grenades too. Class house must write a method to animate an explosion. Inheritance light? I don't want the other stuff. The problem with inheritance is that you've got to take everything even if you only want a small piece. The deal with an interface is you can implement an interface and not have this extra code added to your object. Alright, so let's create a zombie object. Let's take enemy zom1 equals new zombie. Let's draw a picture of zom1. Of course, it's going to have zombie variables and zombie methods. It's also going to have enemy variables and enemy methods. But look there in green. It also has the explode me methods. Remember, zombie extends enemy and implements explode me. Inheritance and polymorphism review. Because zombie extends enemy, it can be assigned to a type enemy reference variable. If a zombie has all the enemy's variables and all the enemy's methods, it could be assigned to an enemy object. If it looks like a duck, walks like a duck, and quacks like a duck, it's a duck. Explode me zom2 equals a new zombie. An interface guarantees all methods, so a zombie object can be assigned to a type explode me reference variable. Yes, you can use an interface as a reference variable type. If a zombie object has every abstract method that can be assigned to an explode me reference variable, see why I call it inheritance light? You're getting a lot of the features of inheritance, a lot of the interoperability of inheritance without going into detail. Now let's do a shape home1 equals new house and build a house object. As a house object, it will have all the shapes, variables, and methods because of inheritance. As a house object, it will have all the house variables and house methods. It's kind of a duh. And finally, as a house object, it's going to have all the explode me methods because house extends shape and implements explode me. A house object is essentially an explode me object. House and a zombie object have little in common except for the methods in the explode me interface. As the word interface implies, it can be thought of as a communications mechanism where two or more unrelated objects like house and zombie can talk to each other by calling the interface methods. Do another one. Explode me home2 equals new house. Here's home2. Variables look the same as the last time. A house object can be assigned to a type explode me reference variable or an array of explode me references. What if we added this method? Abstract public void send message. Now do you see how very unrelated objects can talk to each other through an interface? Any object that implements can then communicate. More code snippets. Alright, let's create a public void method X that takes a vampire obj as a parameter. Here's what we can do with an interface. In the header of method X, it declares it wants vampire object parameters. Now, I didn't write the entire method, but you can assume it will use a vampire object to run methods defined in the vampire class things like object.suckBlood. That's what a vampire does. It sucks blood. This is a call to method X. It dynamically creates a vampire object and passes it to the parameter. It is important to note, per the method X header above, this is the only type of parameter the method will accept. Method X will not accept objects of other types like soldier, werewolf. When you declare a method with a specific type like vampire as a parameter, that's all you can send to it is vampires. In the header of method Y, it declares it wants an enemy object parameter. Now, I did not write the entire method, but you can assume it will use the enemy object to run methods defined in the enemy class. Things like obj.attack or obj.setExposition. There are plenty of inherited and abstract methods, and now we can pass enemy object that extends enemy. We can pass a vampire object to method Y. We can pass a drone object to method Y. We can pass a mutant object to method Y. What we've done is we've opened the door to calling this method with many different types of parameters. Let's look at the call to method Y. This is a call to method Y. It dynamically creates a vampire object and passes it as a parameter. Note, per the method Y header above, it will accept a vampire as a parameter because vampire extends enemy. Method Y will not run methods from the vampire class like object.suckBlood, but it will run the abstract object.attack, which then could execute suck blood. Remember, vampire has its own attack method. If it wants to call a vampire specific method, it can. This is a call to method Y. It dynamically creates a drone object and passes it as a parameter. Note, per the method Y header above, it will accept a drone as a parameter because it extends enemy. Method Y will not run methods from the drone class. It won't say obj.fire missile, but will run the abstract object.attack, which can then execute fire missile. Method Y equals new mutant. This is a call of method Y passing a mutant object as a parameter. It will accept a mutant as a parameter because mutant extends enemy. This is the power of inheritance and polymorphism. Some call this generic programming. We want to write one piece of code, method Y, that accepts many different parameter types instead of writing many different methods. We want to write once and use many. When you code like method Y, you can pass it any enemy object. When you code like method X, you can only send a vampire object. Now let's get real creative. Let's create a public void method Z, and this time let's accept a parameter explode me obj. In the header of the method Z, it declares it wants an explode me object parameter. Now we can pass any object that implements explode me. Again, I did not write the entire method, but you can assume it will use the explode me object to run a method that's defined in the explode me interface. So it's going to do something like obj.doExplosion, because doExplosion was the method defined in the interface. An interface provides the same power polymorphism does without doing full inheritance. Let's call method Z and pass it a new vampire object. This is the call of method Z that's underlined here. It dynamically creates a vampire object and passes it as a parameter to method Z. Note, per the method Z header above, it will accept a vampire as a parameter because vampire implements explode me. Method Z only runs the method from the explode me interface. It'll do an object.doExplosion. But that method is in the vampire class and can run any specific method from that vampire class. Method Z with the parameter new house. This is a call of method Z. It dynamically creates a house object and passes it as a parameter. Per the method Z header above, it will accept house as a parameter because house implements explode me. Method Z only runs the method from the explode me interface. It says obj.doExplosion. But that method is in house and can run any method specific to the class house. See, vampire and house are not related by inheritance, only through an interface. But now I can pass either as a parameter to method Z. Method Z new drone. This is a call of method Z. It dynamically creates a drone object and passes it as a parameter. Per the method Z header above, it will accept a drone as a parameter because it implements explode me. Back to the idea of inheritance as a way to communicate between unrelated objects. When two or more classes implement an interface, it is easy to write code like method Z to send messages back and forth. Method Z, let's pass it a new tree object. This is called a method Z. It creates a tree object and passes it as a parameter. And method Z will accept this tree object because it implements the explode me interface. Back to the idea of generic programming. Write code that does not care what type of object we're using. Do you want to write 10 different programs to create a 10-level game? Or do you want to write just one program that, given a different set of enemy and a different set of screen object, handles all 10 levels? Inheritance, polymorphism, abstract, and interface allow one program to do it. Wow, we're deep into object-oriented programming, OOP now. You may be saying, why do I need to understand this stuff? Why not just learn the Unity game engines? Because this is how Unity works. When you understand how a game engine works, you can program a much better game than someone that does not understand. This is common throughout anything, not just computer science. If you truly understand how a car works, you can repair any car, not just the car you've been trained on. When you truly understand how music works, you can play any song, not just the songs that you specifically learned. Game programming is the same way. The more you understand how objects work, the better a Unity programmer you will be. Power up polymorphism. Methods with the same name. A key to polymorphism and generic programming is methods with the same name. We want to build a set of classes that we know all the methods we can call. So on the left side here we have our enemy object diagram. And enemy is going to declare abstract, attack, and move. So when zombie extends enemy, you know there's going to be an attack and a move method. When drone extends enemy, it has to have an attack or move method. And of course, when vampire extends enemy, it's going to have an attack and move method. Well, what are we talking about here? We're talking about common methods. Methods you can run without caring what type of object the reference is pointing to. Over here on the right side, we have a shape. Shape's going to have an abstract draw method. That means if house extends shape, house will have a draw. If tree extends shape, tree will have a draw. If cloud extends shape, cloud will have a draw method. The compiler guarantees that. Generic programming. What is that? Polymorphism works best when you have methods with the same name, sometimes called generic program, when the code simply does not care the exact type of the object. This slide contains pseudocode, not real code, so I can make it as generic as possible and illustrate the point. Enemy en object equals new some random enemy. The generic random enemy means assign any type of enemy object to en object. The one thing known for sure is it must be a class that extends enemy because it's been assigned to a reference variable of type enemy. You may be thinking, how can I use that object if I don't know if it's a vampire, drone, or a werewolf? No matter what en object points to, it has to have all the variables and methods of class enemy because it's type enemy. If there are 8 inherited methods, This pseudocode call could be running any of the 8 methods inherited from class enemy. Remember, the parent class method should contain the common or shared code. enObject.abstract method. No matter what enObject refers to, all child classes must write the abstract methods declared in class enemy. If there are 3 abstract methods, this pseudocode call could be running any one of those 3 abstract methods declared in class enemy. Remember, abstract methods are written in the child class and contain specific or unique code for that class. enObject.interface method. If, and this is a really big if, all enemy classes implement an interface, you can run the method specified in the interface. That means between inherited, abstract, and the interface, there are 12 methods enObject can execute and not care about the exact object type. An interface does not require inheritance, but it does create a group of objects with at least one method with the same name. The next step is to store and use generic objects in an array. Arrays are used because they have been covered in this course, but there are other options like lists, vectors, and collections that also store objects. Any data structure that stores multiple objects may be used. I'm just using an array in this example because it's what we know. Still using inheritance, polymorphism, and interface, but now utilizing them from the individual slots of the array. This is very generic. This is very pseudocode. This is a terrible way to initialize an array of objects, even in pseudocode. But I need to show filling an array of objects in one line of code. It also shows that all objects in the array must extend shape. This is pseudocode, not perfect code. In a 3D game, this thing would be filled with circles, rectangles, etc., all sorts of geometric shape objects. In a 2D game, this could be a house object, a tree object, and any other object. What we're going to do is just fill this array with objects. Once it's filled with objects, what can we do with objects from each slot of the array? Well, we can say shape array with the subscript slot is an object reference just like enObject. The only difference is you must select which slot. You're going to have to put the slot number in there when you access an array object. Again, this is pseudocode, not perfect code. It doesn't matter what slot or what exact type of object is in the slot, as long as that object extends shape. An abstract method from class shape can be run. That's generic programming. I'm going to go to the object in whatever slot I'm dealing with and run an abstract method. And I know it'll be there because it's guaranteed. For example, if I had an abstract draw method that will allow a simple loop to display the entire screen. Let's use the object in shape array to run an interface method. I don't want this example to give the impression that every object has abstract and interface methods. They do not! When creating a set of related classes out of a common parent class, use abstract. An interface is more for creating a set of unrelated classes that contain methods with the same name. Let's consider the game Angry Nerds, where a bully launches the nerds and tries to knock down a structure. Okay, so Nelson on the TV show The Simpsons played this spoof, but I swear I thought of this before that episode. We want a game with 20 levels, with 20 different sets of nerds, and a different structure to knock down each level. If you write 20 programs, one for each level, you lose. You'll never finish your program. We want to write one program and have it execute all 20 different levels. Now, how are we going to do this? We're going to create nerd objects and have nerd objects inherit from a common parent. So I'm going to say short nerd, nerd2 equals new short nerd. That's not the way to code. Tall nerd, nerd1 equals new tall nerd. That's not the way to code. We want several different kinds or types of nerds. So what we're going to do is create a parent class nerd and a child classes like tall nerd, short nerd, and girl nerd. Do not declare variables using the child classes as this code does, as these 3 lines do. Every level would need to declare a different number and different types of variables, and you're on your way to writing 20 different programs for a 20 level game. Girl nerd, nerd 3 equals new girl nerd. Don't do this. This code would work for one level, which only launches 3 nerds, one of each type. But what about level 20, which launches 4 tall nerds, 2 girl nerds, and 4 short nerds? Declare 10 variables instead of 3? That's bad. We don't want to do that. What we want is a way to declare the number and types of nerd objects so it does not change when the nerds change. That's generic programming. We want an array of nerds. This can handle any combination of 10 nerd objects. I'm going to say nerd array nerd list equals new nerd 10. This one line of code works for all 20 levels. Level 1 has 3 nerds, one of each type. This array can handle it. 7 empty slots, but this array can handle it. Level 20 has 10 nerds. This array can handle it with 0 empty slots. Even better, level 4 could have 4 short nerds, 3 tall nerds. Level 6 could be 7 girl nerds. Nothing in the code changes, even if the nerds do change very much between levels. This one declaration can work for 20 levels of the game. You don't have to write 20 programs, you can write one program. Now you're going to have to load the nerds. I'm going to say nerd list equals load nerd and pass it the level number. At the start of each level, you will need to fill the array with nerd objects. Note the parameter. When it's 1, it puts 3 objects in the array. When the level number is 20, it'll put 10 objects in the array. I prefer using a config file or a database entry to tell my program the number and types of objects. Again, one program that will read a file or database and still work for all 20 levels. Now that only takes care of half the problem. My nerds want to knock down shapes. So I'm going to declare a shape array called shapeList and set it equal to new shape 100. We're going to handle the structure you want to knock down over the same way. We want to build it out of bricks and blocks and walls and roofs and have it extend shape. Then we can declare an array of parent class shape, and you can fill it with any number or type of these objects you're trying to knock down. Early levels of the games will have simple structures, not a lot of objects, easy to knock down. Later levels of the game, most if not all the array slots are used, much harder to knock down. The more shapes that I put in this array, the harder it will be to play a level. And I'm going to say shape list equals load shapes, pass it a level number. I'm going to call some sort of method that will load shapes into my array. Same deal. At the start of a level, read a config file or a database and get a list of shape for that level number structure. This is the structure before you knock it down, when the objects are stacked on top of each other. Once it's loaded, loop through and draw all the objects to display the initial structure. You may need some sort of numShapes variable, not shown, to indicate how many are in the shaped object array. Wish I had more space and more time to cover this design, but I don't. So here are just a few examples. Nerds get launched. Variable J contains a slot number of the nerd at the front of the line. An abstract method launch is used to fling the nerd using the type, force, and angle to determine the path it will take. And importantly, where or if it will impact the structure. I've talked about an abstract method draw before, certainly used at the start of this level to display the initial structure, but also very important when a nerd impacts the structure. The shape will move or fall when this happens, so draw will need to display the shape in a new location when this happens. Shapelist k.fall, an abstract method fall to determine if and how far an impacted shape object will fall. Not gonna lie, this will be a difficult method to code. Many factors like the size and the weight of the impacting nerd or shape, plus gravity, will determine how hard and fast this one single shape moves or falls. Dealing with the domino effect is a realistic manner is going to be key to this method, right? If you can get one shape to knock into another shape, which knocks into another shape, and they draw in a natural and realistic mode, then you have something. Inheritance, polymorphism, abstract classes and methods and interfaces. These are the important object-oriented programming, or OOP, concepts that will allow us to write simple yet powerful code to solve complex tasks. Understanding them is understanding how game engines work, and it enables you to write the best games possible. That's it for this lesson. See you on the next one. Well, I hope you enjoyed that lesson. Once again, I'm Professor Chris Ferguson. Please visit us at gamesci.com to see more interesting lessons.